Hello, and welcome to this video about row operation matrices. Matrix row operations can be represented by matrices. In this video, we'll learn how to write code to make these matrices, and then to see whether or not a matrix is a particular row operation. And then we'll write code to create random matrices so as to test these functions. So the first type of row operation that we'll look at is the row multiplication matrix. This matrix mimics the action of multiplying a row by a constant when it multiplies on the right of another matrix. These are its functions. These create a particular row mul matrix and test whether a matrix is a row mul operation. And this is what a row mul matrix looks like. It is an identity matrix with one of the diagonals being unequal to 1. I'll expand this definition to it being unequal to 0 as well, since this sort of row multiplication operation isn't useful. The second type of row operation is the row add operation, which adds a multiple of one row to another, and here are its corresponding functions. This is an example of such a matrix. It is an identity matrix with a non-zero number in the non-diagonal region of the matrix. This number may also be equal to 1. And then finally, the third type of row operation is the row swap operation. This function swaps two rows. These are its corresponding functions. Here's an example of this sort of matrix. It is an identity matrix that has two 1s in the non-diagonal region and two 0s in the diagonal, so as to perform a row swap. These numbers are marked in red and green. And here's a second example. This matrix doesn't contain any other numbers other than 1 or 0. Now to create the row mul matrix. These parameters stand for variables in the row mul operation. R stands for row, C stands for the constant that we'll multiply it by, and N is the number of rows and columns, since it is a square matrix. We'll firstly construct an identity matrix. Then we'll replace the correct element in the diagonal with this number C. Now to create the row add matrix. This function needs two row numbers this time, and we'll create the identity matrix like before. Then we'll replace one of the numbers in the non-diagonal region by the number C. We've got two row numbers this time, so it's important to get them the right way around. Now to create a row swap matrix. Only row numbers are required. We'll create the identity matrix like before. Then we'll put two 0s in the diagonal, and then two 1s in the non-diagonal region like so. Now to create a function to test whether or not a matrix is a row multiplication operation. This means that we'll have to test whether it has this particular form of being an identity matrix, with one of its diagonal elements replaced by a non-1 and non-0 number. We'll firstly declare this function and its internal variables, and then set the return Boolean variable to be true, and set it to false when we find it not to be this sort of matrix. So it must be a square matrix. If it isn't, then this variable will be set to false, and we won't enter any of the loops. It must be a diagonal matrix, with all of the entries in the non-diagonal region being equal to 0. We must then test to see if this diagonal is like this, with all 1s and one other element being equal to a number that's not 1 or 0. We'll make up this loop. Then we'll count the number of non-1s in this diagonal. We can also set these global constants to be the current row number and number found in this location, so that if it is found to be a row multiplication operation, then we can use these constants to work out exactly which row multiplication it is. If we find a 0 in the diagonal, then we'll return false and jump out of this loop. And if there are two or more non-1s in the diagonal, we can return false and jump out of the loop early. If the number of non-1s in the diagonal of this matrix isn't equal to 1, then we'll return false. And then we'll return the Boolean return variable here to say whether this matrix is a row multiplication matrix or not. Now to check whether or not this matrix is a row add operation, we'll declare the function with all of its internal variables and set the main return variable to true and set it to false if we find a reason to during the cycle of this function. We'll return false if it isn't square. This function is so far similar to the last testing function. We'll check to see if all of the diagonal entries are equal to 1. If not, we'll return false. We'll create a loop to test whether or not there is only one non-zero element in the non-diagonal region. If not, or if there are none, then we'll return false. We'll make up a loop to do this. We'll add up all of the non-zero elements in this matrix, and we'll set these global constants equal to these values so that we can reconstruct what the row add operation exactly is in terms of numbers, if this matrix is found to be a row add operation matrix. If there are two or more non-zero entries in the non-diagonal region, then we can return false and jump out of the loop. If the total number of non-zeros in the non-diagonal region isn't equal to 1, then we'll return false. And here is where we'll return the Boolean return variable to say whether or not this matrix is a row add operation. Now to create a function to tell whether a given matrix is a row swap operation. Here are some examples of this sort of matrix. We'll declare the function with its internal variables and set it to return 1 or true until we can find a condition to set it to be false. And n will be the number of rows and columns of this matrix, because it is a square matrix. We'll count the number of ones and zeros in the non-diagonal region of this matrix, and this loop will do this. These commands circled in red will count up the number of zeros in this region, and these commands will similarly count up all of the ones. We can then return false and jump out of the loop if an element that isn't 1 or 0 is found, like a 2 or 3 for example. And we can jump out of the loop early if more than 2 ones have been found in this region. There should be only these many zeros and ones in this region, and if there aren't, then we'll return false and not enter any more loops. So we'll create a loop to count all of the ones in the diagonal region of this matrix. We'll count the number of zeros in this region using these lines of code. We'll remember the rows and columns where these zeros are located by placing them into this array. It's short for list of ones and can be thought of as storing where the ones go as well. We'll count up the number of ones in this region using these lines of code. We'll return false if a non-zero or 1 element like 2 or 3 has been found in the diagonal. And we'll return false and leave the loop early if more than 2 zeros have been found in this loop. If the number of zeros and ones in the diagonal aren't equal to these numbers, then we'll return false. So we won't enter this part of the code if the matrix is already found to not be a row swap operation. We'll get these numbers corresponding to where we found the ones and zeros from the array we wrote them into. We'll also pass these numbers onto the global row variables so we can reconstruct what the row swap operation was, that is, which rows were swapped. We'll check to see whether these ones and zeros are in the correct locations to create a row swap matrix. And finally, we'll return the Boolean variable saying whether or not this matrix is a row swap operation. Now to test whether these functions work, we'll have to create lots of different sorts of matrices to test them. We'll just concentrate on a few. The random 2-row add function, which creates a matrix that looks just like an identity matrix, but with 2 non-zero entries in the non-diagonal region. And the random 2-row mul function, which creates another matrix that looks just like the identity, but with two non-zero non-1 entries in the diagonal region. We'll create some other functions to help these functions. This function creates an ordered list of non-diagonal entries, so that it will be easy to randomly select one of these entries out of the list. Non-diag X and non-diag Y will contain the row and column of each of these entries, while non-diag lock will contain the location in the array for each of these entries. We'll create a loop to go through all of the entries in the non-diagonal region. We'll get the location and row and column of each of these entries and place them into these arrays, indexed by k. We'll increment k here and start k from 0, so every entry has a whole number associated with it. And we'll set this number to be the number of these non-diagonal entries. So here are some new functions to get a random number between two values for the two different testing matrices that we'll be creating, so as to make them look neater. The first one doesn't allow any random numbers being equal to 0, and the other one doesn't allow any numbers being equal to 1 or 0. The numbers range from L to U, standing for upper and lower values. And here we'll create a jumble function to jumble up a list of numbers so that we can get two random numbers guaranteed to be different to each other. We'll create an ordered list where the numbers in the list are in order and not jumbled. And we'll only jumble the first two numbers given by X. We can jumble more numbers if we like. We'll get a random number from the non-jumbled part of the list. Then we'll swap the two numbers, the one located in the non-jumbled part of the list and the head of this list, and then work our way through the list until we've jumbled all of the numbers that we want. The first X numbers in this list are guaranteed to be random and different. Now to make this function that creates a matrix with two random non-zero 1 numbers in the diagonal, we'll firstly create an identity matrix. Then we'll jumble up two numbers from a list of diagonal locations. We'll get the first random number. We'll get the first random location of a diagonal entry and insert this number into it. We'll get the next number on this jumbled list, which is guaranteed to be different to the first, and insert a random number into its corresponding location in the diagonal of the matrix. And now to create the random two-row add matrix. We'll create an identity matrix like before. We'll jumble up a list of non-diagonal entries. We'll get a random number and the first number on the jumbled list. We'll get the location of the entry in the non-diagonal region corresponding to this number and insert a random number into it. We'll repeat this for the second number on the jumbled list, so then we'll get an identity matrix with two non-zero entries in the non-diagonal region. So now to look at a function that can generate two different row swaps. We'll construct the identity matrix like before. We'll jumble up the first four diagonal entries. We'll get the first two entries from this list that are random and guaranteed to be different. Then we'll actually change the entries from 0 to 1 and 1 to 0 so as to perform a row swap operation. I'll just move this code over to the other side. Then we'll get the next two numbers from this list and create another row swap in this matrix. All of these four numbers are from a jumbled list and are guaranteed to be different. The last matrix generating function is the disjointed row swap. It creates a row swap with one of the ones not in the right position. I do this by generating three jumbled numbers. The first two create the standard row swap matrix, but the third variable gives one of the ones a different column position, which is contained in the variable k. And we can pack these three checking functions up into this one general checking function that can tell us whether this matrix is a row operation or not, and if it is, then which row operation it is. And just another thing I need to mention is that it is necessary to call this function called setup non-diagonal entries before calling the construct random row add matrix function. Otherwise this function won't work. I didn't want to include it inside the function, otherwise it would slow this function down. I decided to show this to you inside this testing function. So I hope that you have found this video helpful and educational, and so have found it interesting because of that. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts in the comments, and thanks a lot for watching.